Hey, yeah, thank you so much for the nice words. So I'm here in my capacity as a software developer for Stream HPC today, and I'm going to talk about my master thesis, which has the similar title as displayed here, which I've done at Heidelberg University. So this is like quite a long title. So first of all, I would like to go through the parts of the title first. Okay, so maybe. Yeah. Exactly. So yeah, first of all, SYCL. I think I don't know how many people are familiar with SYCL from the audience. SYCL is a open source, an open standard, open Chronos standard, royalty-free for targeting GPUs in a cross-platform fashion, utilizing a single source model and like relying on modern C++ as much as possible. So therefore, this is a prime target and nice way to program GPUs if you don't want to get like vendor logged into NVIDIA or AMD or any other platform. And AdaptiveCpp is one of the implementations of SYCL. It comes with right away 2 compilation flows to compile SYCL code for GPUs. AdaptiveCpp can target all of the major GPUs available today at the market, so we can go work on run on Intel, NVIDIA, and both AMD GPUs with both of these models. So first of all, the legacy model, the SMCP compilation flow, is really similar how compilation is handled for AMD through HIP or CUDA, in the sense that the source code is parsed multiple times by the device compiler. For each of them, a device binary is generated, which is done at the end, like linked together into a binary that at runtime will be used to load the right device code to the GPU and then execute there. This approach has a few drawbacks. For instance, it does require on AMD at least to compile for all of the different targets separately. And this can be a problem when deploying code. And then if you forget like a single target, then your deployed binary is not going to work on that GPU. And also it comes with like quite extensive compilation times if you have targeting like a large set of GPUs. And contrary to this, the current recommended approach to compile SYCL code with AdaptiveCpp is the SSCP model, which is a contrary to SMCP. It only does like a single compilation pass, and it relies on a 2-stage compilation model, where in the first stage only a intermediate representation of the device code is stored, which is then later JITted at runtime for a particular device that we are targeting. This has the benefit that we can also include runtime information when JITting the kernel. So for instance, AdaptiveCpp does optimizations based on the aliasing analysis of the pointers that are passed to the kernel. It also includes the workgroup size that we are using, and it does like further optimizations, such as noting how big the entire launch parameters are. And in case that fits into 32 bits, then we are using 32-bit integers to store like thread ID and so on. And it's a nice addition that it also has the benefit that we can just don't have to compile for all these different target devices, but because that's going to be handled at just-in-time compilation time. And finally, the last part from the title is GROMACS, which is a molecular dynamics software package. It solves the Newtonian equations of motions for particles. Usually it's used for simulating biomolecules like proteins, membranes, and so on. It's heavily used for drug research, which is further exemplified by the fact that the main paper of this application has over 27,000 citations. So this is one of those codes that are actually being used for production use cases. And it heavily relies on GPUs, obviously, to solve this problem. So this N-body problem is like very well suited for GPUs. And the reason why this is like a very interesting project for the AdaptiveCpp is that currently the recommended way to target AMD GPUs is through AdaptiveCpp, not through HIP or the vendor recommended binaries, because because GROMACS is using SYCL to target GPUs for Intel and AMD. Yeah, and the reason why we are working on this is that it currently does not use the newest compiler features, so it still uses the legacy compiler. And the scientific question statement was that how much effort would it take to transfer this production code base to the SSCP compiler, and will it be faster, similarly to the benchmark codes that it has already shown that the SSCP compiler is much faster. So the problem between the SSCP and the SMCP compiler, or the effort why we need to do some porting here, is that regular GPU code, usually you specialize code using preprocessor macros. So for each of these compilation passes, the compiler defines a set of macros that contains information about what this code is going to be compiled for. So in our case, this is not possible for the SSCP since we only parse the code once. So there is no for us to have like macros with like both AMD GCN defined to 1 and 0 at the same time. Therefore, the way to work around this is this reflection API provided by AdaptiveCpp, which uses this control flow-based reflection methodology to specialize source code. So technically what we can do here, for instance, is that we can, we can query JIT time information using this reflection API, and this is going to be constant at JIT time, so technically the compiler can just eliminate the branch that is not going to be taken. So technically, this approach has the same effect as if using macros. However, this is based on control flow. So for instance, in situations where the source code uses some macros to change the data layout, this is obviously going to be like a problem, and this is not going to work with this kind of approach. This requires a bit more intensive refactoring. Not to mention that this kind of approach also brings in quite a bit of issues on the device host binary in terms of ODR violations. So it can happen that, like, for instance, in this example, like FCI flow 3 does not mean the same thing on the host and on the device. So this kind of specializing code in this way is also can be quite dangerous and can be quite problematic. So the way we solve this for this particular situation in GROMACS was to implement like an additional abstraction layer where we are passing in a configuration struct and then dispatching it at runtime based on which device are we using the same compile-if API. However, this required like quite a bit of refactoring of this kernel. And this is this non-bounded kernel, which computes the local interactions of atoms, is one of the most compute-intensive parts in the application for big program sizes. So this was like quite an interesting refactor, and we also refactored this obviously for the legacy code path. For the performance evaluation, we were working with like a set of different molecule boxes. So we had boxes from size 6,000 to 3 million atoms, which to my understanding covers most of the simulation size that's used by the researchers in this field. And we also benchmarked different simulation configurations ranging from RF, which reaction field, which only uses a single execution queue in the GPU, and PSH, FSW, and PSW, which are using multiple queues. And these are quite interesting because these include more and more computationally extensive handling of boundary conditions, and therefore they might provide some information about the kernel size. For test systems, I used the MI300X and MI300A GPUs. MI300Xs were used from the AMD Developer Cloud. MI300As were provided by HLRS from the Stuttgart people. And from MI210, I was using the CDNA2 GPUs that we have at StreamHPC available. And so these are the results for the performance. So this is all compared to the baseline is the SMCP legacy code version. And as we can see on MI210, we reach, especially for large problems, like a quite significant up to 25% performance improvement across the board. On MI300A and 300Xs, there are quite significant regressions for the FSW, PSH, and PSW cases. These are the multi-queue ones. And for smaller problem sizes. However, I must note here that these smaller problem sizes below 100,000 atoms are really not well suited for the GPU in terms of not saturating the device completely. Important to note here is that the RF case does not show this kind of regressions on the 300A and the 300X. There we see like a constant 5% performance improvement. So this kind of points to the fact that these regressions are probably due to some runtime latencies, runtime overheads when handling multiple streams, and this is something that's going to be like part of future investigation, hopefully. In this slide, I wanted to show the overall throughput reached by the application in terms of processed atoms per second. So as I already alluded to, smaller simulations obviously have like a slow, generally tend to have like a smaller throughput. And this slide shows the peak simulation performance that we can reach on a single GPU. And we see that this is also compared to relative to the legacy compiler, we reach about up to 10% performance improvement across the board. And last, we were kind of curious about where which parts of the code changes and which parts of the optimizations are resulting in these performance improvements. And first of all, what we saw, which is kind of surprising, is that for the SMCP the refactoring that I showed you for the non-bounded kernel on the first slide, one of the previous slides, does already improve performance quite significantly. So for this non-bounded kernel, which as said, is like it's a very significant part of the computation for larger problems, already that refactoring does give around 18% performance uplift. After that, when we switch to the SSCP compiler, this is the lightest colored red bar, that does not improve performance right away, so that's expected. And by turning on the workgroup size optimization, we reach another 20% performance. And the further optimizations that I mentioned for the JIT time compilation does not seem to improve performance any further. Therefore, these were like grouped into the last red bar on this plot here. So in conclusion, we managed to show that it is possible to port the currently existing code to the SSCP. More involved refactoring also improved code quality and also improved the performance of the legacy compiler. And we also shown that the JIT time optimizations, as already published in previous work, do also improve the performance in production code bases such as GROMACS. So with that, I would like to take any questions if there are any. Thank you so much.
Thank you very much. So time for questions.
Thank you for this committed work. So my question is about a practice that I often see in some codes, that there are some portions of code that are timed on a specific hardware, and then those constants are built into the source for knowing, okay, below this threshold, I will use a smaller algorithm or brute force, above that, more involved one. So can you mimic that in JIT compilation or with your library? I don't say it's best practice to write code like that, but it definitely exists.
Yeah, exactly. I think, I think it's necessary to write code like that usually because it's just like different hardware requires different algorithms. And yeah, sure. So this kind of, it obviously needs some software engineering. So this kind of refactoring, it's very easy now to like introduce with this new config struct to introduce new specialization, like new specializations of the kernels for particular hardware. So yes, it is.
Okay, so could you a bit more elaborate that, please? Because it's not about the features of the hardware, but about that specific hardware. So can you do the timing, like in compilation time or things like that? Thank you.
So you mean like a optimal, like you just select at flight which kernel to choose or which algorithm?
Yes, something like that.
I mean, this is the infrastructure is there, like the features of the AdaptiveCpp allow for this. Like you can, but this is not something the goal of the project to build this infrastructure. So I mean, you could technically build a runtime evaluation on top of this, and then you measure like different kernels and then select the best one, and then just like 4 versions, and then you select the best one that you need.
Thank you very much.
Thank you. Further questions, Donny?
Thank you for the talk. At the beginning, you had a statement like that this SYCL version is the recommended way of targeting AMD GPUs. It was a claim specific to GROMACS. Did I get that correctly? Why is the difference? Is it just more focus or more effort put into this direction, or is there some more fundamental detail or some architecture or software engineering limitation?
Currently, GROMACS has two paths to target the AMD GPUs. There's a heap backend, and there is the SYCL backend. And I mean, in general, the SYCL backend has more features. It's it's been there for longer than the heap port, and it's also, because of that reason, it's also better tested and better supported. And since it has like more optimization went into it at this point, it also has like better performance than the heap version in general. So maybe at some point HIP will overtake SYCL, and then that will be the recommended pathway. But currently, performance-wise, we are still ahead of the AMD version.
Thank you.
So any further questions or remarks to one? Yeah.
Hi, thank you for the presentation. Just a quick question. What do you use for the IR representation of the kernel stuff?
It's VMIR.
Okay.
So that's the reason for that. Reason why I'm not using SPIR-V, because this is like completely internal to AdaptiveCpp. So there is just we're not sharing this. We don't have any compatibility requirements in that sense. So it's just yeah.
Okay. Have you run into any limitations on using LLVM IR?
Not so far.
Okay, thanks.